Take a moment, look around you, really observe the environment you're in. Your phone, that sleek device in your pocket, your laptop, the tool you use for work, creativity and connection, and the invisible network connecting us all, a web of data spanning the globe. This is the digital world, a landscape of information and interaction built on a simple idea, the bit, the fundamental unit of information. Every digital action, every click, swipe, and tap, from sending a message to a loved one to streaming a movie in high definition, is powered by bits, those seemingly insignificant ones and zeros. Think of it as a cosmic Morse code, a language of the universe where specific sequences of bits become, through complex algorithms, letters forming words and sentences, colors, painting vibrant images on our screens, sounds, creating music and immersive audio experiences, and images, capturing moments and creating new realities. Your computer reads and processes these bits, these immense strings of bits at incredible speeds, transforming them into the experiences we enjoy following strict logical rules, the foundation of all computation. It breaks problems into simple sequential steps, a process we call an algorithm, asking yes or no questions, making decisions based on the flow of information, moving through a digital maze one path at a time, searching for the solution. This step-by-step process is remarkably effective for most tasks we ask computers to perform. But what if the maze is unimaginably vast, a problem of immense scale with more paths than atoms in the universe? A truly mind-boggling level of complexity. Even the fastest classical computer, the most powerful supercomputer, would be lost, taking longer than the age of the universe to try every single path and find the answer. Some problems are simply too complex, too computationally demanding for this one path at a time approach, this sequential method of problem solving. To solve them, we must leave behind the world of the light switch, the binary on or off state. We need to journey to a reality governed by fundamentally different rules, a new paradigm of computation, a stranger, more wonderful reality, a realm of possibilities beyond our everyday experience. One where the boundaries of yes and no blur, where certainty gives way to probability, where information isn't just on or off, but exists in a superposition of states. To tackle the impossible, to solve the unsolvable, we need to go quantum, to harness the power of the subatomic world. Welcome to the quantum world, a realm of immense potential and groundbreaking possibilities. Now let's shrink down, smaller than a cell. Imagine diving into the very fabric of life, leaving behind the familiar world of biology and entering a realm governed by entirely different rules. We're not just reducing size, we're crossing a threshold into a place where intuition falters and the bizarre becomes commonplace. A molecule, even an atom. We're now at the scale where matter loses its solidity, replaced by a dance of energy and probability. The familiar laws of classical physics begin to blur, replaced by the strange and fascinating world of quantum mechanics. Welcome to the quantum realm. This isn't just a smaller version of our world, it's an entirely different reality with its own set of rules and possibilities. Prepare to have your understanding of the universe challenged. Here the laws of physics twist, cause and effect become fuzzy, and the very nature of reality is up for grabs. It's a place where things can be in two places at once and where distance loses its meaning. Particles can be in multiple places at once. This is superposition, one of the most mind-bending concepts in quantum mechanics. It's like a coin spinning in the air, simultaneously heads and tails until you look at it, connected across vast distances. This is quantum entanglement, where two particles become linked, regardless of the space separating them. Change the state of one, and the other instantly changes too, a phenomenon Einstein famously called spooky action at a distance. This is a world of maybes, not just yes or no. Uncertainty reigns supreme. We can't know both the position and momentum of a particle with perfect accuracy. The more we know about one, the less we know about the other. For years, this was just a physicist's curiosity, a playground for theoretical exploration with little practical application. Quantum mechanics seemed confined to the realm of abstract thought experiments and complex equations. But then came a radical idea, a spark of inspiration that would change everything. What if we could harness these bizarre quantum phenomena to solve problems that are impossible for classical computers? What if we built computers that harnessed these quantum rules? Computers that could exploit superposition and entanglement to perform calculations in ways never before imagined. Quantum computing isn't just a faster version of today's machines. It's not simply about shrinking transistors or increasing clock speeds. It's a fundamentally different approach to computation. It's a new kind of machine, operating on the fabric of reality itself. It's about leveraging the very laws that govern the universe at its smallest scales to unlock unprecedented computational power. Imagine a classical computer as a piano, playing one note at a time, processing information sequentially, one step after another. It's limited by the constraints of classical physics. A quantum computer is a grand orchestra, capable of playing countless notes simultaneously, playing all notes at once, exploring every harmony simultaneously. This allows it to tackle problems that are simply intractable for classical computers. This ability to process multiple possibilities at once is quantum computing's true power, allowing it to explore vast solution spaces with incredible efficiency. We can't use ordinary transistors here, the tiny switches that control the flow of electricity in classical computers. Instead, we use atoms, harnessing their quantum properties to represent and manipulate information. Or superconducting circuits cooled to near absolute zero, creating an environment where quantum effects can thrive without being disrupted by thermal noise. These are the building blocks of quantum computers, the physical qubits that will power the next generation of computation. And the fundamental unit isn't a bit, the 0 or 1 that represents information in classical computers. It's a qubit, a quantum bit that can be both 0 and 1 at the same time, thanks to the principle of superposition. Let's see what makes a qubit so special, and how it unlocks the potential of quantum computing. A classical bit is like a coin lying flat heads or tails, 1 or 0. All our technology is built on these definite states. But a qubit is like a coin spinning in the air while spinning, it's both heads and tails. Only when we measure it does it become a definite 0 or 1. This is superposition. A qubit holds a blend of both possibilities. Thanks to superposition, a single qubit can hold more information than a bit. Now, imagine two spinning coins, 2 qubits. Together, they can represent all possible combinations at once. Add more qubits and the possibilities grow exponentially. With just 300 qubits, a quantum computer could represent more combinations than atoms in the observable universe. This is the exponential power of quantum information. But superposition is just the beginning. There's another quantum trick: entanglement. Superposition lets a quantum computer, unlike anything we've seen before, walk every path in a maze at once. Imagine a complex labyrinth filled with countless possibilities. A quantum computer, leveraging the power of superposition, can explore each and every one of these paths simultaneously, an ability that defies classical intuition. Classical computers must try each path one by one. They meticulously proceed step by step through each potential route, a process that can be incredibly time-consuming and resource-intensive, especially when dealing with intricate mazes or complex problems. Quantum computers, using qubits in superposition, explore all paths simultaneously. This parallel processing capability is what gives quantum computers their immense potential, allowing them to tackle problems that are simply intractable for classical machines. It's like tuning into every radio station at once, holding all possibilities in a delicate quantum state. Each station represents a different potential solution, and the quantum computer can listen to them all at the same time, sifting through the noise to find the desired signal. This isn't just faster. It's a fundamental shift in computation. It's a paradigm shift that promises to revolutionize fields ranging from medicine and materials science to finance and artificial intelligence. Imagine searching for a book in a library of billions. The scale of the challenge is immense, a daunting task for any conventional search method. A classical computer checks each book one by one, a tedious and time-consuming process, requiring an exhaustive examination of every single volume. A quantum computer can see every book at once, pinpointing the right one in a fraction of the time. This ability to simultaneously assess all possibilities is a game-changer. This is possible because particles at the quantum level exist in multiple states until observed. This fundamental principle of quantum mechanics is the foundation upon which quantum computing is built. By manipulating qubits without measuring them, scientists perform calculations on all possible values at once. This is the essence of quantum parallelism, the ability to perform a vast number of computations simultaneously. Only at the end do we measure, collapsing the qubits into a single, definite answer. This measurement forces the qubits to choose a single state, providing the solution to the problem. Superposition is the key to quantum speed. It's the engine that drives the quantum advantage. But entanglement unlocks even more. It opens the door to even more complex and powerful quantum algorithms. The second quantum superpower is entanglement so strange, Einstein called it spooky action at a distance. Entangled qubits are linked, no matter how far apart they are. Measure one and you instantly know the state of the other, even across the galaxy. This connection is faster than light, defying our normal sense of space and time. It's been proven in countless experiments the universe is deeply connected. In quantum computers, entanglement weaves qubits together. The state of one qubit depends on the others, creating a complex, interconnected computational space. If one changes, the others change too, in perfect harmony. This allows for calculations far beyond what independent qubits could achieve. Entanglement is the conductor, ensuring all quantum instruments play in harmony. The real power of quantum computers comes from these invisible connections. Information is stored not just in qubits but in their relationships. This is the magic of quantum computation. So, how do superposition and entanglement actually compute? It starts with qubits, atoms, or circuits cooled to near absolute zero. First, we put them into superposition, each representing both 0 and 1. Then we entangle them, creating complex relationships. This sequence of operations is a quantum algorithm, guiding the evolution of the quantum state. Think of it like waves in a pond. Some waves amplify, others cancel out. The algorithm is designed to amplify the probability of the correct answer and cancel out the wrong ones. After the algorithm runs, we measure the qubits. Measurement collapses them into a definite state, 0 or 1. Thanks to interference, the correct answer is overwhelmingly likely to appear. The quantum symphony ends on a single resonant note, the solution. That's quantum computation in action. Why build quantum computers? Because for certain problems, they're not just faster, they're exponentially faster. Take factoring large numbers, the basis of modern encryption. Classical computers would take billions of years. A quantum computer could solve it in hours. Quantum computers can sense all possibilities at once, finding the answer instantly. They're ideal for optimization, like finding the best delivery routes or folding proteins. But they won't replace your laptop. Classical computers are still best for everyday tasks. Quantum computers are specialized tools for the grandest, most complex problems. They open new frontiers in science and discovery. So, where are we on the quantum journey? We're in the early days. Think 1940s computers. We've built the first machines and proven the principles work. But today's quantum computers are small and fragile, with only a few hundred qubits. The main challenge is decoherence. Qubits are easily disturbed and lose their quantum state. To protect them, we use elaborate refrigerators and shielding. Quantum error correction is another major hurdle, allowing for longer, more reliable calculations. Every year brings breakthroughs, more stable qubits, better error correction, smarter algorithms. We're no longer asking if quantum computing is possible, but when it will transform our world. The journey is long, but the destination is in sight. We're building the ship as we sail the quantum sea. The future is closer than ever. What does quantum computing promise? The possibilities are vast. In medicine, quantum computers could simulate protein folding, leading to new drugs for diseases like Alzheimer's. They could help design new materials, superconductors, better batteries, or catalysts for clean energy. In finance, quantum optimization could revolutionize investment strategies. Weather forecasting and climate modeling could become vastly more accurate. Even artificial intelligence could leap forward, finding patterns invisible to classical computers. Quantum cryptography could create unhackable communication channels. Any eavesdropping would disturb the signal, alerting users instantly. This means perfectly secure communication for governments, businesses, and individuals. Quantum computing could reshape every aspect of our connected world. The journey to a quantum future is one of science's greatest adventures. The promise is immense breakthroughs in medicine, materials, and our understanding of the universe. But the challenges are just as great. We need millions of stable qubits and perfect quantum error correction. Building these machines is a monumental engineering feat. We also need new quantum algorithms. Knowing what to ask is as important as having the computer. Despite the hurdles, the dream inspires us to explore reality's deepest mysteries. The quest for quantum computing is a quest for knowledge itself. It's driven by the same curiosity that sent us to the moon. Now, we journey into the quantum realm, learning the universe's native language. By embracing quantum weirdness, we unlock new powers. The age of quantum is dawning, ready to reshape our world. The cosmos awaits.